Okay, so we can start on sort of the next part of the lecture, and this is then really moving on to the big data ideas. And so kind of what the first thing that's important to do with big data is to kind of define what does it mean. And so there's often this idea of the three V's. And so this is velocity, volume, and variety. So it's really when you have a lot of data coming in quickly that is very heterogeneous. So where there's a lot of different kinds of data coming in that you're trying to analyze. And so this makes it very different than sort of a lot of the small data problems, whereas when you look at, a SQL database, you have a lot of data, but it's very well structured and everything fits in the same table. Big data then is starting to be where you have lots of maybe different tables or lots of different pieces of information coming in that don't fit into those representations very well. And so what this means is that you need a solution that's sort of performant, scalable, and flexible. And so if you look at, face detection on a CCTV camera in a store, this is performant and scalable, but it's completely inflexible. They have a chip inside that's been programmed once to do face detection, and this runs, on 30 frames a second. It runs in 4K, so it's processing a lot of data, but it's sort of a one-time solution. And if you decide you want to do cat detection instead of face detection, you have to kind of completely re-implement all of the hardware for that. And so kind of big data is when you have problems that fulfill all three of those categories because they require different kinds of solutions than if you only have two of those categories. Performant scalable, performant and flexible works, quite well for MATLAB. That handles a huge data very quickly and lets you kind of change your code or Python very easily on one computer, but it's not very scalable. So when you try to go into much larger problems, you run into limitations very quickly. Sort of the next important key idea from big data is that scaling isn't scary. And so if you have 10, 100, or 1,000 times as much data, it's the same amount of effort for you. And so you sort of build tools and analysis approaches that give you this ability to scale easily. And so if we look at SQL, this has this implicitly. When you go to this query that we had here, select average volume from cells where type equals cancer, this query looks exactly the same if you have 1 cell, 1,000 cells, 100 billion cells, whatever. It's exactly the same query. You don't have to change your analysis because your data volume got larger. But when we looked at the initial code we had before, that required, you say the name of the input file, you say the name of the output file, you then need to run this code on every single file that comes in, and this becomes sort of less scalable. One of the other things is that kind of you're starving for enough data. And so one of the AMP, the algorithms, machines, and people lab at UC Berkeley, and so they're one of the groups that's sort of been pretty innovative in big data, said that your rate limiting factor is always enough interesting data. And so if you're overwhelmed by your data, you're not really in this big data area, you're sort of dealing with it with the wrong approaches. And so for them, it's always getting enough interesting labeled training data is the biggest problem. And once they have that, the computation is easy. The final thing is this sort of the more easily understood is that you really have 0 clicks per sample. And so that everything you're doing is completely automated. You should never have any processes that involve, manually copying things over, manually running sync jobs, starting different processes. All of that should be completely gone. It should really be no interaction from your part, because the way you should look at this is kind of the way you mentioned unit testing 2 lectures ago, is that every time you click, every time you do something, there's a chance you make a mistake. And some people don't like to acknowledge this, but this is provenly true, that every time you interact with something, there's a chance you do something wrong, there's a chance you make a typo, there's a chance you switch 2 files, you switch 2 columns, you add a row where you shouldn't have, and then you end up with data that's incorrect or inconsistent. And so you want to have processes that are as fully automated as possible, because then you know exactly what happened and you can test them. It's very difficult to test to make sure you clicked correctly when you were running it. And so if we start off kind of with the history of big data, and we'll cover this very quickly, that this sort of initially came from Google. So there were researchers in this area doing distributed databases for a long time that would argue that they invented it before Google, but the first people to really do it at scale was Google. And so they had this problem of they wanted to kind of index the internet, and they want to have sort of a nice rank for all the different pages, because even back then there were a lot of junk sites on the internet. And so they wanted to have a nice way of ranking the pages. And so if you have kind of every site on the internet in a list, and you have, a secret PageRank function, then it's, for every site on the internet, current site.rank equals secret PageRank function current site end. Something like this. And so if you want to make this code parallel, that's fairly easy. You have a bunch of computers. Each computer runs, a subset of this list of every site on the internet. And even if you have 1 billion websites, you have 1,000 computers and it's distributed and it runs fine. This is a fairly easy problem. You can use existing solutions to handle this quite well. Even, SQL would do a reasonable job with this. Unfortunately, that's not how PageRank works. Does anyone know how PageRank works? How does Google decide if websites are good or bad? Yeah?
Doesn't it kind of look at how many pages link to that page and how many pages this page links back from?
Yeah.
From that, it calculates the activity or the rank.
Yeah, exactly. And that sounds very easy to say in one sentence, but it means that this whole approach doesn't work at all. Because it means you can't have some secret PageRank function. It means you need to look at every other page to see if it links to this page. And so now we end up with these kind of nested for loops, where you have to go through kind of every site on the internet, and then go through every other site on the internet, and you see if it's linked, and then you add it to that PageRank, and if it's not linked, then you don't. But now, this is a very difficult problem. How do you divide this task up? Any ideas? So kind of the easy way to divide it up, or one of the easy ways to divide it up, is if you have a small list of websites and doing this computation is expensive. You could have a copy of all of the websites on every machine. And every machine then just runs a subset of the list there. So you end up with a much smaller list on each machine to go through, and your PageRank might take a long time to run, but you can distribute it that way. Of course, that's not the reality. The reality is PageRank runs fairly quickly, and you have lots and lots of websites, and so one of the things you can do is try to divide it up. And this is what happens in SQL sort of automatically, and it's called sharding. And this is where you break up your sites or your database into kind of separate sections, which aren't really interdependent. So if you had, English sites, Chinese sites, Indian sites, Indonesian sites, that you could probably divide your data up fairly reasonably without missing out on too much. Of course, if you have a Chinese site linked to an English site, you won't see that if you've split it up that way, but you at least have some more ability to parallelize it. And, another solution is to buy a really, really big, really fast computer. And this is one of the things Google tried, of course. They don't necessarily like making new software for no reason at all. And they found that on sort of the most powerful computer they could buy, this code took a month to run. Just one loop. And this sort of is only the beginning of the story because, PageRank doesn't just count. PageRank actually looks at what the PageRank is of the site that's linking to you. And so if you have sites that are linking to you that are high quality, your rank goes up. And if you have sites linking to you that are low quality, your rank goes down. And so that means this whole process is now iterative. So you have to calculate the rank for all of the sites, and then you have to update the rank for all of the sites based on the first rank you calculated for all of the sites. And then you have to update it again and again and again and again. And so if you have iterations to run, you now take the most powerful computer in the world, and it takes 12 months to update your page rank. In that 12 months, you now have 200 million new websites that aren't included in your index. This would be incredibly inefficient. And so Google started building sort of piecewise solutions to this problem. How can we implement specific algorithms very efficiently? But they found kind of as soon as you make a change to one of these things, you have to change not only your PageRank algorithm, but also all your distributed and parallel code to make this run efficient. You then also have the problem if one computer or hard drive crashes. How do you get computers to jump in? How do you solve this issue? Because the reality of Google is there's earthquakes somewhere, there's power outages, you have lots of different issues. And how can you make a generic solution to solve big problems like this? Well. And so what they came up with is this idea called MapReduce. And so basically what they do is they divide all problems into two classes. And they say, all of the large-scale parallel programs we're interested in right now are made up of map steps and reduce steps. And so if we can make a tool that takes a data set, a map step, a reduce step, and where to save the output, then we can kind of solve a number of different problems using one fixed tool. And we have that one tool that knows how to do maps really well on thousands of computers. The tool knows how to do reduce operations really well on thousands of computers. And then it can bring it together. And so rather than having to define in our PageRank how distributed computing works, we simply break up PageRank into a map and a reduce, and now have those run really efficiently inside of another tool. And so a map function is sort of, if you use Python or functional programming languages, this is a common idea, but it's basically just a function that returns one element for every element you give it. And so that, your map function could be x squared, and if you gave it a list, 1, 2, 3, 4, 5, f of x is x squared, then the map function from f on L would be 1, 4, 9, 16, 25. And so basically what the important part of a maps function is that it's linking one input to one output, so that it has nothing to do with the neighboring elements or the other elements. It's just focused on one element. The reduce is sort of the more complicated function, and this involves sort of aggregating a number of different elements together and then summarizing them. And so, for example, to sum up all the different elements, that reduce function would be sort of g of a and b is a plus b. And then so when you run this on your data, you get g of g of g of g of g, 1, 2, 3, 4, 5. And so what that would give you is the sum of the squares of the input that you put in. And so now you have, if you've made a tool called MapReduce that handles this problem of, giving data, giving a map step, giving a reduce step, you now can compute the sum of squares on millions and millions of data points without any additional effort, because the MapReduce handles reading the data, writing the data, distributing the computation, making sure a computer's restarted if it crashes, making sure you have all the outputs correctly calculated, and you only worry about how you define map and how you define reduce. And so if we look at it, you sort of take the L, the MapReduce tool, which is what Google calls it, sort of divides it into different chunks. You then apply map to each element. You shuffle, repartition, and group the data. Then you apply reduce to each group. And then you collect results and write them to disk. And basically, in this paradigm, you now can define a task by the data, the map function, and the reduce function. And so it makes very complicated tasks very simple to describe. One of the important ideas for this is this sort of key value pair. And so here we didn't have that. We just had a bunch of individual elements. But often your map spits out key value pairs. And so you have the key, which would be sort of the first index, and the value, which would be the second index. And so often your first index would be like a number, the second index would be like a string. And so this comes in for like counting words, which is one of the common examples given, that if you have a folder full of text documents and you want to find out what word is the most frequent, you can take and have your map step basically take your strings that you give it and split it up into key value pairs, where the key is then sort of dog or car or whatever the word might be, and the value is the number of times it appears. And so you end up with cat 1, dog 1, car 1, dog 1, car 1, dog 1. And then you sort of have a shuffle group step, which takes all the keys and sort of brings them together. So cat is now 1, dog is 1, 1, 1, car is 1, 1, 1. And then the reduce step, which you basically say is sort of x plus, add all the elements that are in the same groups together. And then you end up with cat 1, dog 3, car 2. And sort of these intermediate things you don't need to worry about as much. You basically have the ability to solve problems at an enormous scale very easily. And so this makes solving large problems very simple, because rather than having to think about all the distribution tasks, you can focus on how do you make your algorithm fit into the MapReduce paradigm. And once it fits there, you have tools available to scale it up. And so Hadoop is sort of the name of the first tool, and this came from Yahoo, to perform MapReduce outside of Google. So MapReduce is sort of the copyrighted name that Google has for their tool internally, and Hadoop is the name for this that you can install on your own laptop easily. Hadoop then implements a lot of these MapReduce file functions that you can run, and this has been used at scale with thousands of different machines to process, petabytes of data. One of the other things that MapReduce does really well is that it moves the computation, which is usually very small, to the data, which are usually very big. And so when you think about how you normally do kind of cluster computing, you normally have something where you read in your data on your machine, you do some processing, and then you save the data back. With MapReduce, you send the process, so the map command and the reduce command, to the nodes where the data is saved on their local hard drive. They then read the data from the local hard drive, run the map command, run the reduce command, save the data again to the local hard drive. And so you never have to copy the data to your computer. You simply deal with the data in a very distributed manner. And so this can make computations, particularly when you're looking at all the websites on the internet, much faster, because you don't have to copy it all to one place first. And you don't have 20 different machines or 1,000 different machines trying to read from the same data point or the same drive at the same time. And so those are kind of the factors that make this kind of a game changer for how you deal with algorithms in sort of a large distributed space. So Spark is sort of the follow-up to MapReduce. And so this is what came out of this AMP lab, and it's sort of a much more general tool for doing not just MapReduce commands, but running directed acyclical graphs. And those are one of the things that we talked about in the first lecture. If we go all the way back here. Pretty sure we talked about it here. So we had this sort of idea that we talked about before, very similar to what we did with kind of the soup metaphor, because that we talked about in the first lecture, where you basically have a directed acyclical graph for the soup that we made, where you kind of have your final step and you have arrows which point down, which connect your different steps together. And so this is how you express sort of the interdependency of tasks that you have by making this graph explicitly show what's required, so that you can't boil without having both this red and the hot water. And you can't wait 5 minutes after the soup until you've sort of combined all these things together. And so this is how these sort of pieces fit together so that you can express a workflow in a very independent manner. And so this is important for big data, but it's also exactly the same construct you use for tools like TensorFlow and deep learning, is that you specify this graph and another tool decides how that computation should be efficiently done. And so this is kind of the whole basis for TensorFlow, and one of the exercises will kind of show you how to make a very easy graph there, where you can then make this graph and then tell it, run this on the GPU, run this on the CPU, run this on 20 machines distributed, because this graph is really independent of what your exact data set is or what your problem is. This graph basically just shows how you get from your inputs to your outputs. And it allows for a lot of this parallelism and caching to happen from the system rather than you manually implementing it. And so Spark does sort of the same thing. It takes one of these graphs. You then define the graph. You have a number of different operations you can use. And this then offers sort of the in-memory caching, the sort of fault tolerance, and the scalability that you need for running this at a really large scale. So you don't have to worry about the logistics or how everything's organized or what's being saved at what time. You just worry about specifying this graph for the task that you're trying to accomplish. So for cloud computing, the sort of idea here is that the scalability of computers in a research lab or a cluster is quite limited. If you have 20 nodes in your cluster, to get another 10 nodes would require a budget of thousands or hundreds of thousands of francs. Where with cloud computing, you have the ability to sort of rent computer resources on demand when you need them to solve a specific problem. And so you have the ability to kind of access machines that are automatically set up. You have sort of virtually unlimited capacity and storage. And you usually have sort of cluster management and everything else built in. And the ability to use the same exact setup as many different people. So if you use Euler's cluster at ETH, and you have a collaborator in Japan and they want to run the same analysis, they won't be able to use Euler. They'll have to set up their cluster and hope that they get the same versions of the same tools and that it works well. And when you use cloud resources, a group in Japan can have exactly the same infrastructure as you and get the same results. And so it makes a lot of these tasks a lot easier. It's also quite relevant for sort of energy savings in that, if you have one computer sitting in your office, it's very likely underutilized. It's often very heavily utilized during the day when everyone's there. And then overnight, unless someone's running a huge job, it's just sitting there. And so this isn't a very useful way to make the most of these resources. And with cloud computing, you have the opportunity to have machines that you're using during the day, and then at night, because you're sleeping, but people in China are awake, they can be using the same resources. And so you have sort of this sharing economy benefits. So if you look at sort of future imaging goals, this was just a simple graph that we had, where if you were looking at how many gigavoxels you could process per hour. This was measurements we've done at sort of one of the beamlines at the Paul Scherrer Institute, where you sort of have on this scale, your laptop in sort of this bottom left corner, sort of the baseline for what you can process on one machine, to kind of what you can process on a powerful workstation, to what you can process on like a small group cluster, to what you can process on sort of the full group cluster, to the full sort of institute computational level, to kind of having access to the CSCS supercomputer, being able to use all of the resources there at the same time. And so these are sort of a brief overview for specific problems that we were trying to analyze of how much you could scale up your analysis and what the sort of relative computational needs were. And so the scaling isn't quite linear, it's sublinear because you have more and more expense as you have more nodes being used that have to communicate, but it's fairly linear in that sense. And so you have the ability to see kind of how much analysis you can do with how much computational power and where sort of the standard nodes fit in there. And of course, with cloud computing, you can't probably get quite a full CSCS machine in the cloud, but you can certainly get clusters that are much bigger than sort of the institute-sized clusters for small periods of time. So I think I'll leave this out at the moment. This isn't particularly relevant. Yeah, so this is just a computational example of some analyses that we've done before, where you can take something that would take, single core, 360 minutes, 6 hours of computation, and do this now on a cluster in a distributed way in 10 minutes. Or get sort of a single k-means iteration on some of your analyses in 1 second rather than 2 minutes. And so, of course, when you shift to that scale, for explorative studies, it's very relevant because if you have to wait 2 minutes to get feedback, you're not going to play around with an analysis very much. And if you can get a result in 1 second, it's much more interesting. And this makes sort of iterative analysis and hypothesis testing much easier. This is then even more true with approaches like deep learning, where you want to try out a lot of different approaches and a lot of different architectures and a lot of different networks, where if you have sort of one machine on a single core, that can be quite slow. And when you have a really powerful GPU or a cluster of machines, you can now iterate through these models much quicker, which gives you a better ability to pick out the best model rather than taking the first algorithm that finishes and going with that. So in terms of Spark, if you're interested in learning more about that, we'll have a few links to this in the exercises for how you use this. There's a course in the informatics department next semester, which will use Spark quite a bit. There's also other projects which are very similar, where you can use, one's called Flink from Berlin, and it offers much of the same functionality. It's just a slightly different tool. But it's definitely worth checking out. The data I've sent, the link I sent you yesterday, I don't know, had anyone signed up on Databricks Cloud or tried it out? So that basically what it gives you is the ability to run anyway. Anyways, with that, you have the ability to sort of use one small cluster that's already set up with them in the same way you use Kaggle. And so you can analyze small data sets, you can see how the tools work, you can play around with it and see how relevant it is for your application without having to go through all the setup procedures of getting it running. And so particularly for kind of playing around with some of these different analyses or seeing how distributed computing works or how well your algorithm fits into that model, it can be quite useful. Of course, once you've done this static analysis in sort of batch mode, one of the very interesting things to do is sort of streaming analyses, where you now take all of the analysis you're doing and run them in sort of real time so that you have constant input coming in and you have tools set up that allow you to run the analysis on 10 different nodes so that the computational results are finished as quickly as possible and give you feedback so that you can make decisions on what you're doing right now. And so this can be relevant for sort of experimental settings where you're heating a sample and you're not sure if you've heated it too much. And you can use a 3D structure to give you feedback on how you should be heating it. It also can be applied to sort of other things where you have sort of a real-time camera that's looking at the weather and doing some sort of analysis to update predictions. And one of the nice things about these sort of new generation of big data tools is that you can use the same analysis that you make for a static one-time batch job to run on a streaming job. And so you have this ability to transition away from a single process to looking at things in real time as they're coming in without redeveloping everything. And you can scale just as well by connecting more computers and starting workers on these computers very easily. One of the other sort of very interesting results is the ability to do kind of approximate analysis, where rather than trying to get the perfect result, you try to get the most accurate or the best result you can with a given time constraint or accuracy constraint. And so with this, you could, if you're looking at thousands of samples and you want to know what's the average volume, you can say, give me the best average volume in 5 seconds. And so it will give you an estimate for the average volume as well as sort of the error bars, what's the confidence interval for this value. And this can be then quite useful for making decisions where you don't necessarily need a perfect result, you just need a reasonable result. You can also then say, give the best volume within a 95% confidence interval so that you can get that result very quickly rather than waiting for all that computation to finish. So that covers it for this lecture, unless there's any questions.